everybody, and welcome to our talk about high-performance packet parsing in OVS. Today, Kumar, Amber and I will tell you about how we used AVX512 for Miniflow extract and protocol-specific hashing. Specifically, we're going to talk about Miniflow extract in the context of AVX512, and we're going to talk about some protocol-aware hashing that builds upon the previous AVX512 optimizations. Jumping straight in, what is a Miniflow, and what does Miniflow extract actually do? It parses the input packet. So when OVS receives a packet, Miniflow extract is executed, and it will parse the packet, extract some metadata, and build a structure called a Miniflow. This Miniflow is used throughout OVS for classifying packets and for mixing or understanding what switching actions to take. This can take some time, so Miniflow extract can consume some CPU cycles. We'd like to optimize that using SIMD instructions to make it go faster. As part of that, we took some time to really design optimized code. The reason this was required was because there are quite a lot of traffic patterns that are available or that customers often use when deploying OVS, such as various combinations of Ethernet, IP, IPv6, UDP, TCP, etc. When designing this code, we had two things we really needed to scale. The traffic patterns or traffic profiles, so Ethernet, IP, UDP, etc., but also CPU ISA, so that you could implement a new version of this particular piece of Miniflow extract code and have it easily integrate with the existing optimized code. So validation and testing of this are also very important to ensure that we have confidence in the correctness of the implementations. We designed some code here as well called auto-validation, similar to how previously DPIF and Miniflow extract and DPCLS have been implemented, in that we can automatically validate the optimized code against the existing scalar code to ensure that their operation is identical. So if we look at the OVS data plane as a whole, on the bottom left we see packet RX using DPDK, we see the DPIF selector, which is going to execute our data path glue code. We're going to have a Miniflow extract selector, which is added in a patch set that this work is represented here in this patch or in this slide, where the DPIF netdev can essentially use different implementations of the Miniflow or Miniflow extract. In this particular case, DPIF netdev /Miniflow parser set will change the implementation of Miniflow extract at runtime. This allows us to test both the scalar code as well as the AVX512 code, but also to select the auto-validator, which will ensure that all of the implementations that exist are actually performing the same optimizations and the same output of the Miniflow, resulting in confidence in their operation and that they are correctly parsing the packet. In order to understand the optimizations and the code design that we're describing in this particular slide deck, it's useful to understand the basics of AVX512 and how we optimize using AVX512. AVX512 allows you to take 512 bits or 64 bytes of packet data, so essentially an Ethernet header, an IP header, and a UDP header will all fit in 64 bytes, and to put that data, so the values themselves, into a single register, a ZMM SIMD register. This allows us to operate on all parts of that packet with a single instruction. So single instruction, multiple data, SIMD is the operation really and the basis of this optimization. Here we can see on the top a packet representation using the purple block, and it shows a particular input packet that OVS has just received. We also see two other values, so a mask or a protocol mask in blue, as well as what we refer to as hit values or protocol values that we can match against. The way that OVS in this SIMD code is classifying packets is by doing a bit mask, so a bitwise AND operation with a mask on the packet, and then comparing the results to the protocol values themselves. By hard coding these masks and values, we can support specific traffic patterns, so very common ones such as Ethernet, IP, UDP, Ethernet, IP, IPv4 in this case, TCP, things like that. And we can have the code be very, very optimal for handling that specific traffic pattern or that specific traffic type. What actually occurs if we hit, so if the protocol values after matching or after masking the packet match the protocol values exactly, then we can provide a shuffle instruction with specific input values for that protocol. The shuffle is indicated here by the pink arrows in various directions. The result of this shuffle is the data from the input packet, but now in the layout or in the shape of the Miniflow data structure. What that really means is that we've taken an input packet, we've applied a single bitwise AND operation to that entire packet, so 64 bytes that we are bitwise ANDing, and then we're comparing it to protocol values. Again, that's a compare equal across each byte in that entire 64 bytes of register. And that gives us a value which is either going to be a hit or a miss. If we hit, it means that we know the exact packet layout of that input packet, because we knew, or by probing the packet, we've realized that it's an Ethernet, IPv4, and then UDP packet. Because we now understand the entire packet layout from L2 and L3, it means that one shuffle instruction is actually sufficient to transform that input data into the shape that the Miniflow expects it in. To be clear here, there's a very direct relationship between any specific input packet and the resulting Miniflow. The scalar code executes this step by step and parses protocol by protocol. In SIMD code, however, specifically AVX512, it's possible to contain so much of the packet headers in a single register, so 64 bytes at a time, that we can optimize across protocols and across Ethernet, IP, and UDP, and in one set of instructions, so one bitwise AND, one compare, and one shuffle, we can actually transform all that data from the input packet to the Miniflow result. That's the fundamental optimization that's going on here. And it's enabled by the fact that AVX512 registers can consume so much of the packet headers in a single register and in a single shuffle instruction. So to elaborate a little bit more about exactly what these protocol mask, protocol values, and shuffles actually do, let's imagine we're processing an Ethernet IPv4 UDP packet just like before. The protocol-specific data here is a protocol mask, so this is a bit mask that indicates what part of the packet are important to have specific values, and if those bit masked parts of the packet have those specific values, it means we understand the entire packet layout. That's the fundamental concept to understand. If we mask and then match the protocol values, we understand the entire packet layout, which means that it's then valid or correct to apply this shuffle, which again matches the protocol. So the shuffle, the mask, and the values are all for a specific protocol stack, so either IPv4 UDP. And those three combined allow us to really optimize and gain performance here. That's to build the data part of the Miniflow data structure. So I refer to them as Miniflow blocks in general, so a block of data in the Miniflow. So the actual values themselves, if we had a MAC address of OXFFFFFF, then that would be the data being stored there. However, the Miniflow also contains a field that I refer to as Miniflow bits, and this indicates what is present in the Miniflow. So because we've already matched on this specific set of protocol items, either IPv4 UDP, we know what Miniflow bits to set, because there's a hard mapping between that and the Miniflow bits. So the input packet, again, has a very strict mapping to exactly which Miniflow bits are set. What that means is any packet that we receive and match, we can hard code and basically write down the Miniflow bits based on our understanding of having matched this packet by the yellow compare, or the compare to the protocol values as indicated in yellow. Also, the DP packet properties, so in this case packet lengths and L2 or L3 offsets, are known because we understand the entire packet layout. So a lot of value and a lot of optimizations are actually based on the fact that we can do a protocol mask and then match it against the protocol values. And if we hit in that particular protocol pattern, we can then know the Miniflow bits, we know the offsets, and we know exactly a shuffle that will transform the data as required to become a Miniflow from the packet, from the input packet. What's very important here is that this is all static data. So per profile, so per ETH IPv4 UDP or Ether IPv6 TCP, this is all static. So we can mask away a bunch of bits from the input packet. we have values, and then we apply a shuffle. And regardless of exactly what traffic pattern that is, it's actually possible to transform that in a static way. So we know what values the shuffle will need to transform that data correctly. And that static data is something that we optimize against a lot in the code. So that's why this is really an interesting way of approaching the problem. Because by designing optimized code, we actually remove a lot of complexity from code in terms of instructions and move that complexity instead to an area that's more akin to static data. So it's compile time, constant data that the compiler can then use and put into the instruction stream. Let's talk a little bit more about that. So fundamentally, we don't want to rewrite all of the Miniflow processing for each particular traffic pattern. So ETH IP UDP, ETH IP TCP, those have a lot in common. We don't want to have to rewrite AVX512 code and revalidate and re-verify it for every single different traffic profile. What we've done in this case is we've written one Miniflow extract, so MFEX, in this case a generic function, and it takes a profile. So it takes an integer ID, which represents either the top number 0 or the middle 1 or the third diagram here on the right, and it indicates those using what we call a profile ID. And it's just an integer, it represents that particular profile. This allows us later to call the generic function with different functions called, for example, Miniflow extract IP UDP, Miniflow extract IP TCP. By marking the Miniflow extract generic function, as previously introduced, the larger function here in this slide, marking that with always inline in the OVS codebase, or attribute always inline in GCC attribute annotations, we force the compiler to always inline the code that is contained in Miniflow extract generic into the lower boxes here. So as we can see, the inline kind of arrows take the IP UDP protocol values, take the generic implementation of Miniflow of the MFEX generic function, so the code from the generic function, and the specific protocol stack as indicated by the integer profile ID, and inlines both of them into the bottom left gray box here, Miniflow extract IP UDP. What does this mean? Fundamentally, the compiler now has a lot of context. It knows exactly what static data will be accessed. It knows exactly which instructions will be executed on that static data in the Miniflow extract generic, and it can create a single optimized function, which is Miniflow extract IP UDP, in an extremely optimized way because it does not handle generic profiles anymore. We've told the compiler at compile time that MFEX generic, we want to call that function with the value 0, we want to force inline it, and that means that the compiler can unfold a whole bunch of branches and things like that. There's actually a huge switch statement in Miniflow extract generic, and that all disappears. So in these optimized functions at the bottom, we end up with pretty much optimal code for that particular profile, despite that we never wrote that code. We wrote a generic version of that code, and we let the compiler do its optimizations. And the compiler pulls all of the constant data out of our ETH IP UDP constant data section of the code, and inlines it and uses it in the instruction stream itself. So fundamentally, instead of hand coding an instruction stream, which would be very verbose and require a lot of manual testing and more human effort in terms of producing that code, this method of specializing the function, so Miniflow extract generic gets specialized into Miniflow extract IP UDP and Miniflow extract IP TCP. So we've created two optimized functions from a single generic function by force inlining and by passing a constant value for the profile ID. So this is a really advanced software optimization technique that can be applied across data plane software in general. And here we make extensive use of that as well as static const data to get the most performance we possibly can. It results in something like this, that Miniflow extract generic never actually executes. That function does not exist in the OVS binary because it is always inlined into Miniflow extract IP UDP, which will execute on the data path, is specialized to a profile, and can be specialized to CPU ISA. And that is the real value of writing generic code and having the compiler optimize it for us. Lastly, we should talk about auto validation and testing. So the auto validator clones packets and validates them against different implementations. So the scalar implementation of Miniflow extract will run on one version of the packet. We've cloned the entire packet burst, we run it through the optimized Miniflow extract, and then we compare the resulting two Miniflows. This allows us to ensure that all of the Miniflow contents are bit for bit absolutely identical. That gives us high confidence in the correctness of our Miniflow extract optimization, or of the SIMD optimized AVX512 code, ultimately. If the auto-validator fails, we can dump all the data for debug. That means the developer needs to come and fix whatever issue there was in the code. Somehow a packet was not being processed properly. However, in the majority of cases, and absolutely the case in any released OVS binary, that auto-validator must always pass, and we just continue processing. Lastly, because we have some infrastructure in OVS for good unit testing, we can actually fuzz test this particular Miniflow extract auto-validator. So we can provide fuzzy packets, so input that is fuzzy, so randomized, and run our Miniflow auto-validator against both versions of that packet. And that gives us even higher confidence that this will actually correctly process any version of an IPv4, UDP, whatever packet that it matches on, and it will give you the correct results. Now let's talk about protocol-aware hashing.
Hey everyone, so I'm Kumar from Intel, and I will be continuing this presentation on how do we optimize hashing in OVS. So OVS uses the software-based RSS hashing, and to do that it needs IP addresses, L4 ports, and then the protocol itself. Now in OVS, as of now, the hash function itself is a complex one. And why so? Because the hash function is not aware what it is going to get. And to know that, it then does all the comparisons like if else and so on, but causes jumping. And what it is trying to find out is whether its L3 is an IPv4 or an IPv6. And same goes for L4 as well. Now, even if it is known that, okay, I am having an IPv4, then again, it has to fetch it from someplace, right? And then it will go to fetch it from an MFEX blocks array, which is again a complex thing and not so good as well. So how do we optimize it? So we are trying to optimize it by using the pre-knowledge which we gain from AVX512 MFEX. And through that, we have tried to optimize the hashing, removing all the if-else branches, removing all the unwanted access to MFEX array. So how it is happening? So the first thing which AVX512 based MFEX does, it will try to segregate and find out what is there in the packet header. That means it will say you exactly whether it actually contains an Ethernet, whether it contains an IPv4 or an IPv6, whether it has an L4 or not. So once we know that exactly what our header actually contains, we also know where are those infos which we need for hashing. We call them offsets. So we are going to send both the info to the hash itself. So the hash doesn't have to care about what is there inside the header. It can directly use those offsets to go in the packet header itself directly without going to any other foreign array, and then fetch what it needs, like I have shown here. And I'm combining both of these things. This is how we have tried to optimize the hash itself. No branches, no foreign accesses, and everything is just based upon the offsets. So no comparisons at all as well. And how have we gained the overall performance? First, instead of processing one element of the header at a time, let's say first Ethernet, I will do something with it, then it will be an IP, I will do something with it, and then it will be a UDP, and we will do something with that. We do not do that anymore. We are processing the entire header itself. So whether it contains an Ethernet, VLAN, IP, or an UDP, we are going to play with the whole set. We are not going to process it one by one. And how? Using the AVX512 based instruction set. And afterwards, again, by using the profile aware hashing, we have removed all the branches in the code. We are not doing any comparison. We are not fetching it from a foreign array. We are just speeding up everything in the hashing as well. And the best part, all the code is already available on OBS for you guys to have a look at it and maybe try it out. And for any comments, feel free to come back at us. We will happily address it, and we have a target in mind that we will upstream this patch in this 2.17 itself. And thanks a lot, guys. For any question, you can anytime contact me or my colleague Harry, and we will happily answer it. And I'm a good luck, guys, and have a great day ahead.
All right, let's thank Harry and Kumar for their talk. I believe that we have both Harry and Kumar on hand to answer questions. Would you like to come on to video and audio and say hi?
Hey guys, hi everyone.
Oh, welcome, Harry. So we don't have any questions that have popped up yet. Do either of you want to say a few words before while we wait for some to pop up?
Yeah, sure, we can chime in. So first of all, there's been a few revisions of this Miniflow extract. For those who attended last year's OVS Conf may have seen a somewhat similar talk with somewhat similar colored diagrams. In this particular case, there was a kind of a change in angle on how we actually approach the implementation. So in the middle of the talk, we talked a little today about how this specializing and real performance is gotten from this approach to the code, and how the static data is laid out, how that kind of ties together with SIMD instructions, and you can get very high performance code. Previously, we had approached it in a more generic fashion, and although that generic fashion seemed very interesting, it ultimately did not result in the same performance benefits. So as a result of that, we kind of redid some of the design of that implementation and went for a more performant, ultimately, solution by looking at specialization. And then, yeah, Amber, I don't know, would you like to discuss any more of the profile hashing, how we figured that one out, and the differences in iterating mini flows and just pulling the data out of a packet directly?
Yeah, so it was so we realized the thing after some time, like when we were doing the MFEX part, then you and me actually realized that we can extend it to hashing as well, and then we decided to move on with the hashing part, and then we added the things one by one, and now the patch I'm currently as of now, so we found that we can optimize one more part of it, and then the V4 of it will also contain that optimization as well. And we are not actually completed yet, Harry, right? So we will be coming up with more and more, whatever we see that we can optimize it with the AVX512. So yeah, so we will bring all those to you.
So we're starting to get some. Go ahead, finish your thought.
No.
So we're starting to get some questions in the Q&A panel. So let me read off the one that appeals to me the most. So Logan Blith asks that, or says that there can be a penalty when a CPU switches to SIMD instructions. Is that true? And if so, is that penalty small enough that SIMD is still a good choice for this application?
Great question. And there's two answers. There's the short one and the long one. I'll start with the short one. Yes, there is still benefit to SIMD. And I can talk a little bit more about the long one if we like. Really, the punchline comes down to, do you use enough SIMD? So if you issue a tiny few SIMD instructions and then do a lot of scalar processing, then there's a small cost to pay because you're using more transistors. That generates a little more power, etc., or power usage, I should say. So there has been concern about that in the past, and there has been some misunderstandings really around when and how to deploy things like AVX512. So I'm really happy you bring up this question because it allows us to set the record straight. With the first slide that we showed with the DPIF, Miniflow extract, DPCLS, and now actions also coming up in the next talk, the AVX512 will actually be running all across the data path. So everything, including DPDK PMDs now, also have AVX512 code paths, which can be enabled with a force minus max SIMD bit width option to DPDK's EAL. So there's some really cool stuff now that you can actually, with the addition of the actions patch set, receive from a network card, process in your data path glue code, process and parse the packet, understand using a wildcard classifier, and modify a packet all in the AVX512 domain. And that just gives huge performance benefits. So great question, and I'm glad it's asked. And yeah, interesting definitely to investigate where we can apply more AVX512 ultimately, because we're not stopping yet. I see there's another question that came in, Ben. Will I let you read it? I think Ilko was asking about more traffic profiles.
Yeah, why don't you go ahead and answer that? In particular, he was asking about OVN Kubernetes-like traffic patterns and whether you have any traffic profiles to match that.
So fantastic question. You guys, as part of the OVS conference, are very familiar with various workloads and various traffic profiles that you care about. I am a software optimizer. I do my best to understand networking, but ultimately I'm a software guy. What that basically means is please reach out to me and say, Harry, I want you to go and optimize this traffic pattern because it matches my Oven Kubernetes profile, right? So please do take this right here as an offer of, I will help you. I will try and understand your workload and we can optimize this together. So absolutely, yes, Ilko, fantastic. Thanks for asking. We will investigate Oven Kubernetes like traffic profiles, but please also state this on the mailing list or drop me an email. Let's open this up to the OVS community, understand what traffic profiles people care for, and then let's go and optimize those.
That's a great answer. I have to say that personally, when people ask me, have you tested against this? My answer is usually, well, do you have something I can work with, because I don't have that data. It sounds like you're kind of in the same boat.
Yes.
And then finally, Ilya asked if you have performance numbers, because he didn't notice them in the talk.
Correct. There's no performance numbers in the talk. As you know, performance can wildly vary from different deployments and different configurations. It's very difficult to get a representative workload that everyone says, nods head, yes, I understand what this means for my deployment. Encourage people to run it themselves. If Aries peeps are very interested in a specific thing, you can try reach out to us directly. We might be able to help you. Ultimately, benchmarking it in your own deployments is going to tell you your performance numbers best.
Great.
Good question as well.
So it's time to move on to our next talk, which also